This is a magnet. If you have been studying magnetism, you probably know that only certain metals are attracted to a magnet. These metals include iron, nickel, and cobalt. A magnet will not attract a copper penny or aluminum foil. One end or side of a magnet is labeled the North Pole. The other end is the South Pole. The red side of this disk magnet is its North Pole, and the black side is the South Pole. The opposite poles of a magnet attract, while the like poles repel. The reason one end of a magnet is called the North Pole is because that end of the magnet is attracted towards the Earth's North Pole. Here is something you can try. Hang a magnet on a string so that it can rotate freely. After a while, the magnet will stop spinning. The North Pole of the magnet is now attracted toward the north. A compass is a device that uses a magnet to determine directions. The small red and white bar in this compass is a rotating magnet. The red end is the North Pole. Once it stops moving, it will be pointing north. Another magnet brought close to the compass repels and attracts the magnetic compass needle. Now that we have taken a quick look at magnetism, let's examine an interesting relationship between magnetism and electricity. If you have watched our electricity video, you will know that electricity is a flow of atomic particles called electrons. Electricity moves from the minus end of a battery through a conductor, usually a metal, toward the plus end. In the summer of 1820, a Danish scientist, Hans Christian Oersted, made an amazing discovery while investigating electricity. Oersted didn't know what electricity was, but he knew that if he connected a metal wire from the minus terminal to the plus terminal of a battery, the wire heated up. In 1820, he was demonstrating this to some friends when he noticed something very strange. Every time he connected the wire to the battery, a compass needle close to the wire would move. Oersted had discovered a relationship between electricity and magnetism. When electricity flows in a wire, a magnetic field appears. This compass needle moves every time I complete the circuit. If I keep the circuit closed, the compass needle locks into position and the short wire gets hot. The discovery of this relationship led to the development of many important devices, including electric motors and speakers. We are going to construct an electromagnet, a magnet that is powered by electricity. To construct this electromagnet, we need some iron. This 4-inch common nail is almost pure iron. It is a good idea to make the nail safer by filing the sharp end. We also need some wire. We are using 5 meters of 28 gauge copper wire. First step is to wind all of this wire onto the nail. Start with one end sticking out about 15 centimeters. Be sure to leave this end exposed. The winding doesn't have to be neat, but make sure you keep winding in the same direction. Cover about 1/2 of the nail with the copper wire. When finished, leave the other end of the wire sticking out, also about 15 centimeters. We are going to connect our electromagnet to a AA battery, but before we do that, we have to remove some of the insulation from each end of the wire. This type of copper wire has a clear insulating enamel covering the outside. Electricity can't flow through this enamel. This forces the electricity to follow the wire from one end to the other and not jump across from one part of the wire to another. Sand about 1 centimeter at each end. This exposes the copper metal inside. We are ready to test our electromagnet. When I touch it to this pile of paper clips, nothing happens. But when I attach a AA battery, we have a powerful magnet. You can use an elastic stretched around a AA battery to connect your electromagnet. Push the wires under the elastic at the plus and minus ends. Here is something else interesting about electromagnets. Like a permanent magnet, they have north and south poles. Bringing a compass close to the tip of our electromagnet, we can see that the red end, or north pole of the compass's magnet, is attracted towards this end. We know that opposites attract, so this end of our electromagnet must be its south pole. The compass confirms that the other end of the electromagnet is the north pole. We know that electricity, flowing electrons, moves from the minus end of the battery toward the plus end. The electricity moves from this end of the battery, through the coil, back to the plus end. Let's see if changing the battery connections affects the polarity of our magnet. Remember that the tip of our electromagnet is its south pole. Flipping the battery over and reconnecting, we see the tip becomes the electromagnet's north pole. The direction that the electricity flows through the coil determines the polarity of the electromagnet. You can change the north and south poles on an electromagnet by reversing the battery connections. If you decide to build an electromagnet like this, make sure you have adult supervision. This electromagnet must be constructed with a 4-inch common nail, 5 meters of 28 gauge insulated magnet wire, and one AA battery. Never use any battery larger than a 1.5 volt AA battery. With a single AA battery, the electromagnet will get warm. A larger battery could cause the coil to overheat. You can modify this electromagnet so that it has a handle and a switch. Full instructions for adding a handle and a switch to your electromagnet can be found at our website, hylaroad.com. Follow the project's link.